The cycle itself is air, which continuously circulates in a closed loop and always behaves as an ideal gas. This one is actually very important. Why is that the case? If you think about it, so far, all our properties change, all our your internal energy change, all the enthalpy change, they are all based on one single substance only. We talk about water, we talk about R134A, we talk about air. We only talk about one substance. But as you can see just now in the reciprocating engine, that is actually not necessarily the case, because we do have air and we mix it with fuel, and then combustion happens. That is actually the main issue. So far what you learn is, if you have one substance, temperature increases, properties change. That is all. So those property change are due to the substance own change due because of the temperature. But when you have things like combustion, then we involve chemical reaction. Then there is a whole set of different energy change involved, because you have chemical reaction, then you have chemical energy, that kind of thing. So because you have break of bonds and then different types, then you involve a lot of different types of substance. So for example, something like this. So let's say you have carbon. If you're burning a carbon with O2, then what you get is like CO2, right? So then if you just look at this, then you know that you are no longer working with just pure air, which means that then what you learned so far will not be applicable anymore. So for here, we try to approximate it to something that's simpler. Obviously, it's not going to be accurate, but they are usually close enough that we can just ignore those changes. So, because ultimately, who cares about, I mean, like if you are selling your car, for example, who cares about what's the efficiency of the engine, right? You are the one who care about it. So it is just for you as a benchmark, usually. That's why it's okay for us to do this kind of approximation or simplification. So for air standard assumptions, the very first one is that we have working fluid. The working fluid is pure air. We don't deal with anything, and it behaves as an ideal gas. Number two, all the processes are internally reversible. So this was where we try to assume that it is ideal. Then the combustion process is replaced by a heat addition process from an external source. So number three is actually carry forward from one. Actually, four also same thing. Because number three, because now that your air, we no longer mix in with fuel for combustion. So you no longer have combustion process, right? So now you imagine it like how you are trying to boil your water. So now you are trying to heat up the air. That's all. Then exhaust process is also the same, because now you no longer have exhaust, you don't release that, right? Then now you are imagining it as you are cooling down the air instead. So these are the four main air standard assumptions when we are dealing with gas cycles. Of course, you need to know what they are. If I ask you what are the air standard assumptions, then you need to know what they are. But when you are writing the assumption for the analysis, you can just write that this cycle works on air standard assumptions. Then it is known that it is understood that it is based on these four assumptions. Meaning, when you write assumptions, your usual steady flow process, you write air standard assumptions. You don't need to write out all four. Okay, so there are of course two more where it's actually air standard assumptions, but we add a bit more words there. So we look at the second one first, which is what we call air standard cycle, meaning just a cycle that works based on air standard assumptions. Very straightforward. Then there's another one, which is what we call the cold air standard assumptions, which I thought I changed the value, but never mind. So this is when the working fluid is considered to be air with constant specific heats at room temperature. So meaning, remember, we have constant specific heat, we have variable specific heat. And for constant specific heat, even though we call them constant, but usually different temperature will still give you slightly different value. So when you use cold air standard assumption, we just keep it at room temperature, which actually room temperature to have fixed value one. Here the book say 25, but I would say 27. Why do I say 27? Actually, the 27 part is actually for this, where is it? Again, it doesn't matter whether it's 25 or 27. The main reason why I changed it to 27 is because of this. You have one table here for 300 Kelvin. So you can use this directly. Because if you use 25, then probably you need to come to this table, then you interpolate between this to get a 25, which is 298 Kelvin. So if it is 27, then you can use the value from this table directly, which is table A2, where you have properties for all of these different type of gases. For you, most probably you only need gas. So you can get this value for 300 Kelvin based on here. So this is the property. So that's why I say 27. Actually, it doesn't really matter. The keyword is room temperature. The value don't change too much on to it. Okay, so now, so one more reason where we can just assume the working fluid is air is that, so for air composition, mainly is 25%, 21%, I think. I sometimes get confused between their mole percentage and their mass percentage. Something along this line. Is 20 something and 70 something. So for air composition, mostly we assume this. All the other stuff are very, very, very minimal, or even carbon dioxide. That's why we don't want so many of it in the air. So in combustion process, this thing usually remain inert, meaning it doesn't change. Which is also why then you can just assume that the entire thing is air, because only like 20% of it will be reacting with the surrounding. Okay, so now that we have established these assumptions, we look at the actual engine cycle. So SI engine, or the spark ignition engine, gasoline engine, works on what we call the Otto cycle. Sorry, there's a lot of names. I don't know why they have to give them so many different names for the same thing. But yeah, so the cycle that spark ignition engine works on is what we call Otto cycle. Okay, so the actual cycle, if you draw it on a PV diagram, it should look something like the first graph, which is the one on the top. And if we use air standard assumption, we idealize it, then the ideal cycle will look like the one at the bottom. Okay, so now we look at the first one first. So the first one, again, actually you have looked at it, you have studied it just now in the video. So the first one shows you what an actual 4-stroke spark ignition engine is and the corresponding PV diagram. So what happened to the air fuel mixture. So the first one, it actually starts from a compression stroke. So during compression stroke, you have air fuel mixture inside. The crankshaft will push or compress the air fuel mixture. So you can see from here, this is where it happens, so roughly around here. So when you reach this point around there, the spark plug will ignite the air fuel mixture, combustion will occur. So during the moment that the combustion occurs, okay, then the PV diagram will go all the way to here. At that exact moment. So you can see that at this moment the volume only changed slightly. But of course, right after the combustion, then the gas will expand. Then it will push the crankshaft down, right? So this is the expansion process. You go all the way here. So the expansion process will go all the way until it reaches the BDC, which is here. Then when it reaches the BDC, this exhaust valve will open. And when the exhaust valve open, we will expel all the exhaust out. So during that process, the exhaust will be expelled. Then when the crankshaft reach the TDC, then exhaust valve will close. Then intake valve will open. Then it will take in more air fuel mixture. Then compression stroke will happen again. So then this will go on in the cycle. So you can see here, this is my intake valve open, then again this is the intake where at the same time it will push the, so when you take in the air fuel mixture, at the same time it will push the piston back down to the BDC. So that is how it all goes. So you can see from this figure, during the exhaust and the intake process, then the pressure is approximately the atmospheric pressure, because at that moment the exhaust valve and the intake valve are open, and which is also why I said we are actually approximating it as a closed system, but it's not entirely a closed system, because during that process we are actually opening up the cylinder so that we can take in and expel the gas. So that is the actual process that takes place here. Of course, based on this actual process, if you just look at this graph, you will see that it's impossible for you to analyze this whole thing properly, because there are too many variables here. If you want, you need to have a sensor like every single position and every stage in order for you to analyze this properly, which is not feasible. So the idealization will be as at the bottom. So the compression stroke, we will approximate it as an isentropic compression. Okay, so during that process, the compression is isentropic. There's no heat exchange involved in the case. So then compression, then it goes this way. So when it reach state 2, or when it reach the TDC, then remember our air standard assumption. I say that we no longer use combustion. We assume that you are just heating up the air. So it is an heat addition process. And during that heat addition process, again at that moment, since it is just heat addition, there shouldn't be any change to the air, at least at that moment, right before it expands. So we say this as a constant volume heat addition process. So once the heat addition process is over, then we assume that only the air expands. So during the expansion, then we get an isentropic expansion process. To 4. Then when you reach the BDC again, this time instead of the exhaust valve opening, we are cooling the whole thing down. So we are rejecting heat. So then this will be a constant volume heat rejection process. So these are the 4 processes that after idealization, the one that we use to analyze the cycle. Okay, so based on the idealization, we can actually draw a TS diagram as well. So you are expected to know how to draw this graph. Okay, so and then what processes take place during that moment. So you can see the first process 1 to 2 is isentropic compression. So in essence, it is actually a work addition process as well, a work in process. Then 2 to 3 is constant volume or isometric heat addition, so Q in process. 3 to 4 is an isentropic expansion. So expansion process is usually a work out process. So expansion process in most cases are the process where we generate work, because you are pushing the piston will move other things, and then that thing will generate work. So expansion process are usually the work out process. And then after that, lastly, constant volume heat rejection, so Q out. So this whole thing can be translated to a TS process as well, a TS diagram as well. So this is the work in pro. So here, this will give you work in, while this will give you work out. Okay, so you can also see that the relationship between these two graphs. So there's a very funny thing here whereby, now if the curve, we just use the term curves lah. If you see that the process is a linear line at one graph, it will be a curve at the other one. It usually goes this way, because if you just look at ideal gas equation PV over T, it cannot be everything also constant, right? Two of them must change. So which is why if one thing is constant at one graph and the other graph is a curve. This one I will show you a bit more in the tutorial, whereby in tutorial you will have two questions, the first two questions where you need to actually draw out PV diagram, TS diagram, just based on the processes that I tell you. There will not be any process that you have learned. I mean, like, it will not be like this. This one, so let's say if I ask you to draw an auto cycle, the diagram is fixed. So make sure you know how to draw this. Meaning, they should look like this, with the work out, work in, Q out. Okay, so the four processes here, again, isentropic compression, isometric heat addition, isentropic expansion, and lastly, isometric heat rejection to complete the cycle. So the only process that don't exist here in the actual part, meaning in the actual cycle, is actually this one. Because compression is compression, just that we approximate it as isentropic. Expansion also same thing. Heat addition is the combustion process, but we call it heat addition process here, that's all. But in the actual engine, we don't really have a heat rejection process, right? We actually have an exhaust process. We just expel the gas, that's all. But yeah, and then we refresh a new one. So in a way, it is still a cycle because the beginning is still the same, because the air fuel mixture that you put into the engine is still the same air fuel mixture. So it still restarts in a way. So but after our idealization, we don't have this exhaust process anymore, right? So but we still want it to go back to the initial state so that we complete one full cycle. That's why then now we add a heat rejection process, which is also why I say this heat rejection process is the one process that doesn't really exist in the original state. It's something that we add so that the cycle can be completed. We can connect state 4 back to state 1. Otherwise, this part is just an empty spot, which is actually the actual case lah. If you think about it, in the actual case, here we put in exhaust here, and then here this is intake, and then there's nothing here actually. It doesn't really exist on that. It's just imaginary. Okay, so now we look at how we can analyze the thermal efficiency of this cycle. Why does now, since we know that we are modeling this based on closed system, right? So if we are modeling this based on the closed system, this is one slide that I haven't changed, but never mind. Since we are modeling this based on a closed system, let's look at, you see, we know that thermal efficiency is work net over Q in, and we can actually model it as 1 minus Q out over Q in. So here we focus on how to find out Q out and Q in, but technically speaking, the same technique can be used to find work in and work out as well. You will get the same answer. Okay, now when I say I didn't really change is this general equation. So you can see that actually we say Q in minus Q out plus work in minus work out. But again, I think you should know this by now. It is actually the same thing as minus work out minus work in, which is what you learn it for your case. Okay, but same thing. So essentially, since this is a closed system, we just say that this is Q minus W equals to delta U, or that general equation in that case. And like I said, we want to find Q in and Q out. So for Q in process, it's just a heat addition process. And since we are assuming that it is a constant volume heat addition process, which means that you can cancel work in and work out because there will not be any boundary work. And it is a heat addition process, you cancel Q out. So essentially you are left with Q in equals to U3 minus U2. So for variable specific heat, and if you are assuming that you have a constant specific heat, meaning if we are using, let's say, cold air standard assumption, then you can use CV T3 minus T2. Again, this is something that we will look at later on. So for this chapter, we actually have two methods. One is variable specific heat, one is constant specific heat method. So again, two variation lah. And also I told you this before as well. C delta T is actually only for air, so you can use this equation here. Okay, so this is Q in. So unlike what you learned for refrigeration trainer cycle, so that time we say that all the change in the energy is actually delta H. But here, since we are dealing with a closed system, the change in energy here is delta U. And then, since we found Q in, then we can find Q out. So for Q out, we follow the same process. Now, Q out is 4 to 1. We cancel Q in because we want Q out. Once again, it is a constant volume heat rejection process. So we cancel work in, we cancel work out. Then you are left with delta Q, negative Q out equals to U1 minus U4. So since this is negative, we change it to a positive case, then it becomes 4 minus 1 instead. So when you are analyzing cycle, most of the time you will know that which one is Q out, which one is Q in. So just keep the value to positive. That will do. Okay, so even though we don't show here, like I said, similarly, let's say if you want to find work out, we know that this is work out and this is work in, right? So similarly, actually you can just find work out with U3 minus U4. You can also find work in with U2. Why this I don't let me write? Always. So you can also find work in with U2 minus U1. It's the same thing. So you can still keep to work net over Q in equation, but then then a bit more work. You need to find two more things. I mean one extra things. But if you try to analyze this, like for example, maybe for your own study, you try to find all of them, you will see that it comes to the same thing. Okay, so same. So now for this chapter, there is actually one very simple way to look at this. If you have no idea what the question is asking for, but you see that I'm asking for auto cycle, for example, but you have no idea what the question wants, you don't know what to do. Find the temperature and internal energy for every state. Because either way, you can see that you will have some use for them. So even if you don't know what to do, you just stop there and you find all the internal energy, temperature. You will have solved maybe about 50 or 60% of that particular question. So this is one key takeaway lah. If you don't know what to do, just find all the internal energy and the temperature, or every state, for every state. But of course, that's provided that you understand how to find them lah. But if you don't, then the whole question cannot do. Alright, so this is the general case. So when it is variable specific heat, everything is again from table. So that we will see in one example. Okay, so now we want to again further derive certain equation here for thermal efficiency. So for this equation here, something is missing. This slide is for constant specific heat only. Or rather, maybe I write this, it is better this way. This slide is only for cold air standard assumption. Or constant specific heat lah, again. So constant specific heat, which actually is also obvious because you can see that we start the derivation based on CV delta T. Okay, so when you have a constant specific heat equation, when you have a constant specific heat case, thermal efficiency 1 minus Q out over Q in equals to 1 minus CV delta T over CV delta T. Very obvious, right? So then this CV can be cancelled off because the specific heat is constant. So once you have cancelled them off, now you can see the next step of our derivation. We take out the T1 term and we take out the T2 term. Okay, so that we are left with, so that we have a ratio inside. So why do we do that? In this case, so now we recall that when we idealize this process, we say that the compression and expansion process are isentropic, right? So process 1 to 2 and 3 to 4 are isentropic, and we also know that volume 2 is equal to volume 1, volume 4 is equal to volume 1 because of the constant volume processes. So you can see from this diagram also, we say that these two lines are the constant volume line. So what can we do here? So you recall back last week's lecture, we derived this relationship for when we have ideal gas, constant specific heat, and when we have isentropic process. And I mentioned that these relations are only applicable when the process satisfies all three criteria, which is the case in this case. When you assume cold air standard assumption, then we are talking about ideal gas and constant specific heat. And so we apply this to the isentropic process, which is process 1 to 2 and 3 to 4. Okay, so meaning we can safely say that T1 over T2 is equal to V2 over V1 K minus 1. And since we know that V2 and V2 is equal to V3, V4 is equal to V1, then we know that they are equal, right? If they are equal, then it means that T1 over T2 is equal to T4 over T3, which gives us this. So why do we do this? Because we want to derive a relation for the thermal efficiency of the Otto cycle when we are assuming constant specific heat. So the thermal efficiency of this one, okay, we skip a bit more steps, but you can see that if these two is the same, now we come back to this equation. It means that this can cancel off, right? So which also means that the thermal efficiency of the Otto cycle can be modeled as follows. So here we change the V, so the volume ratio or the compression ratio, we use a simple word to replace it with it, which is R, and K here is the specific heat ratio, Cp over Cv. If you come from fluid background, then this K is actually the gamma that you learn in fluid. It's the same thing. So then we have this equation where if you have a Otto cycle that is working on cold air standard assumption or constant specific heat, you can actually find the thermal efficiency directly through this equation. Of course, this is not going to be applicable if you have if you are dealing with variable specific heat, but the value shouldn't change too much. So this is also sometimes an equation where you can use to cross-check your answer essentially. Okay, so sometimes if you do not know how to find T, you don't know how to find U, you can use this equation to find out what is the thermal efficiency as well. But of course, it won't be a full marks lah, but at least it will be something that you can use to find out the final answer. So this is more of a cross-check equation. Okay, so again, this is only the equation that is only applicable if you have a constant specific heat case and if you have a cold air standard assumption. Then this equation has one more use actually, which is this. So based on this equation here, because now we have the thermal efficiency of the equation, we have the thermal efficiency of the cycle in the form of compression ratio, right? So you can actually see that the thermal efficiency of the engine is not directly related, but I mean it is directly related to the compression ratio. I was going to say proportional, but it is not. It's directly related to the compression ratio. So based on this, you can actually draw a graph, plot the graph, to see how the compression ratio is affected, how the thermal efficiency is affected by the compression ratio, as well as the specific heat ratio. So here, based on this graph, we are just talking about different gas. This K value actually will be differ based on different gases. So if you are compressing different gas, then you get different thermal efficiency. And then here on this side, you get compression ratio. So, on this side, then this is the main effect of compression ratio on thermal efficiency. So you can see that the higher the compression ratio, the higher the thermal efficiency is. But of course, there is still a bit of, the increase will reduce, meaning the higher it is, then the more you increase the compression ratio, then the less of the increase of the thermal efficiency is. So the typical compression ratio for the gasoline engine is between 8 to 11 for the reason mentioned when you watch the video just now. Because we say that gasoline is actually very volatile, so it burns very easily. So if the compression ratio is too high, when you're compressing the FU ratio, again, we know that pressure increases with temperature, meaning the higher the pressure of the gas is, the higher the temperature it will become. So since gasoline is very volatile, if you are compressing, if during the compression process, when you reach a too high temperature, the gasoline might ignite before your spark plug works. So more like a premature combustion. And that's what we call the engine knot. Okay, which is something that we don't want. Which is why gasoline engine cannot go to a high compression ratio. So yeah, so then here, I said K is different gases. So for normal air, standard air will be K equals 1.4. 1.667 is the monatomic gas, meaning gas with a single atom. Okay, so here we look at one example. Today, today I will stop at this example. So meaning you learn how we can solve this example, then we are done. Okay, so we are solving an ideal Otto cycle here. So let's read the question. An ideal Otto cycle has a compression ratio of 8. So this is so here you need to note down that you have an ideal Otto cycle and you have a compression ratio of 8. So you are given R equals to 8. At the beginning of the compression process, meaning state 1, air is at 100 kilopascal and 17 degrees Celsius. So you have R equals to 8, P1, and then P1 equals to 100 kilopascal, T1 17 degrees Celsius. 800 kilojoule per kg of heat is transferred to air during the constant volume heat addition process. So Q in is 800 kilojoule per kg. During the constant volume heat addition process. So accounting for the variation of specific heat. So this is keyword. Usually the question will tell you whether we are looking at a variable specific heat or a constant specific heat. These two will have a slightly different method. So here I'm only showing you how to use the variable specific heat method. Okay? So determine the maximum temperature and pressure that occur during the cycle. So meaning we are looking for this point. Right? That state 3 is where you get a maximum temperature and also maximum pressure. After that, network output, thermal efficiency, mean effective pressure. So all those things are what you learned today. So essentially you can see here, as long as you know how to analyze state 1, 2, 3, 4, B, C, D, they are all soft, they are there, in a way lah. Okay, so like I said, if you don't know what to do, we find all the U first, or T if it is constant specific heat. So we look for all the U first. Now, what information that we have here? We have the compression ratio, we have everything for state 1, we have Q in. So we can start from state 1, obviously. So we start with air standard assumption. We start with the assumptions here. So the first assumption, we say air standard assumptions. Like I said, this is the important assumption for this chapter. So air standard assumptions. Then, as usual, KE and Z, the closed system, so KE and PE are negligible. Number 3, you can write, you can don't write, because the question usually will tell you. But of course, if you write it down, it serves to remind you which method you can use. Okay, if in the off case where the question doesn't really tell you whether it's variable or constant specific heat, then it's up to you which one you want to use. But very unlikely that will happen. Okay, so for the variable specific heat method, okay, now one keyword that you can remember is this. Variable specific heat method is table method. Constant specific heat method is equation method. Meaning constant specific heat, you can calculate everything based on equation. Variable specific heat, you need to use table. So we go to table. You have seen this table some time ago, but we didn't really focus on how to use it lah. So you go to your table, you go to table A17. You can see it. Oh, very small. Okay, go to table A17. You can see it is a table for ideal gas properties of air. Okay, so this is the table for air, ideal gas properties for air. For this table, you will see that, so for air is actually very dependent on temperature and temperatures only. So, one lucky thing here is that for air, right, unlike when you're dealing with water or R134 air, you don't actually need two properties. What you need is temperature. So everything is based on temperature. So once you have temperature, you have H. Enthalpy, you have internal energy, you have this entropy value that you learn in second law. Now, we have one P value and one V value here, but you need to keep in mind, they are not pressure and volume. These two terms are not pressure and volume. Air can exist at any temperature and any pressure or volume. These two, let's see what are the terms that they use. So the term that this table uses is relative pressure and relative specific volume. You can also think of it as like reference volume or reference pressure. It's just something for us to compare. Later you see how we use. So they are dimensional quantities used in the analysis of isentropic process. They are not the actual pressure and specific volume. Okay, again, I'm just reminding you that. Okay, so we go back to the lecture notes first. Now, what we do here is this. State 1, we know that it is 17 degrees Celsius. So 17 degrees Celsius will give you 290 Kelvin. So very straightforward. You just come to this table, you look at 290, this is a U. So while you take down the U value, you note down 676.1 first, which is the VR value. Okay, so you can see from here. So using data from table A17, you note down the U value and the VR1 value. Okay, so how do we make use of this VR1? We say that it is not the specific volume, right? It is the relative volume. So what we can do is this. Even though VR1 is not V1, but we can say that their ratio is the same. Just like what you did for Carnot cycle. You say that their ratio is the same. So V2 over V1 is actually 1 over R, because we learned that the compression ratio is 8 in this case. So the compression ratio is the maximum volume over the minimum volume, meaning V1 over V2. Can follow so far? So from here, you can calculate the value for VR2. So far, okay? Okay, then I hope you can see where this is going. Since just now, state 1, we look for VR1, right? So now we got VR2, so what you do? You go back to the table. You look for VR value now. So it was 84.51. So at the VR value, you look for 84.51, which doesn't exist here. So you have 81.89 here, you have 85.34 here, so what do you do? Yeah. So you have to interpolate. So here, then, so your value, your temperature should be between 650 and 660. Since it's 84, it should be closer to 650 lah. And you can see here, the value here is 652.4. And then, so you need to do 2 times interpolation here. Because you need both temperature and internal energy. If you don't need the temperature, then it's fine. But in most cases, you will need both. So here you need to do 2 times up. You need to get the temperature, you need to get the internal energy. So this is interpolation. So we are done for state 2. Okay, clear so far? Okay, so now is the issue. So now, to be fair, right, this question, you don't really need to find the temperature if the question didn't ask for maximum pressure. Okay, you will see why that is the case. But because technically speaking, you can find U3 now, right? Because the question gave you Q in. You have Q in, you can find U3. Because Q in is just U3 minus U2. So we skip the first part first. We look at the second part. So what we said just now. You are given the heat addition term. You are given the heat addition term. So based on the heat addition, you can get U3. Okay? So you can get U3. So why do we need the temperature 2 just now? Because the question asked for P3 as well. So you need to go one by one. So meaning just now you found T2, then now you need to find P2, which is what you did at the top. So based on ideal gas equation, we know that PV over T equals to PV over T. So now we have T1, we have T2. We also have this ratio. Then you can find P2. Okay, so this is just extra. If it is only on the energy analysis, you actually don't need the temperature and pressure anymore. Okay, so after that, rinse and repeat. You found U3, right? And what is the process between 3 to 4? So 3 to 4 is again an isentropic process, but expansion process. Meaning you repeat what you did for state 1 and state 2. But now slightly different lah. So you found U3. Well, U3 is 1275.11, then do same thing again. For U, you look for the U value. So it was 1275.11, so again it is between here and here. This is U. See here? So then again you need to interpolate. So based on this interpolation, you can see that we can get temperature. Then at the same time we find VR3 again. Because then we can just solve this based on that. So anyway, you found T3, then we can find P3. Okay, once you found T3, then you can use the ideal gas equation again, this time between 2 and 1. So this is the ideal gas equation between 1 and 2. This is ideal gas equation based on 2 and 3. Then based on temperature, you can get the pressure. So this is the pressure that you are looking for actually. So this is part of the answer. So this is also the answer, T3 and P4. Okay, so part A asks for the highest temperature and pressure, so these are the answers. But of course, your work is not done here because you still need to find out what is the thermal efficiency and other stuff. So meaning, like I said, you need all the U. Right? So now you have VR3. Since it is also an isentropic process, you repeat the same thing as what you did between 1 and 2. So now between 4 and 3, we know that V4 and V3 is equal to V1 over V2. Here you can also see it over here. The pressure, the volume is the same. This is also why. Now, so for me, right, usually when I solve cycle type of question, even if the question don't ask, usually I will ask you to do so also lah. I will always sketch out the either PV or TS diagram first, because this diagram actually serves as a guide on how you can solve the question, because you can see sometimes you don't remember when the volume is the same and stuff. When you look at the graph, you can see that it is actually there. So from here, again, repeat, you can find VR4. Then come back here again, 48.864. Then for VR, you look for 48.864. So again, more interpolation. So it's between the 800 and 820. Okay, but this time, technically speaking, you don't need to find this anymore, because you don't really need T4. What you need is U4, but of course for your practice U1 you can find T4, doesn't matter. So all you need is U4. Then once you have U4, you can calculate Q out, which is this value. So then you can find work net based on the difference between Q in and Q out. So like I said, work net you can also find through work in minus work out. Sorry, work out minus work in, because work out will always be higher, which is actually so this is actually U2 minus U1. This one is actually U3 minus U4. So again, they are the same thing. If you just put in Q in minus Q out, you will see that they are the same thing actually. This one is just U4 minus, very hard to write here. This side usually cannot write one. So yeah, if you just put in U4 minus U1, U3 minus U2, you will see that you balance them out, you get back the same equation. So it's the same thing. You can do either way, whichever one that you are comfortable with. Okay, so then you are done with work net. So then with the work net over Q in, then you can get the thermal efficiency. Again, you don't need to find work net also. You can just use 1 minus Q out over Q in. It's the same thing. So here, let's say if we use, so the second part is not necessary. We are just proving it. So if you use cold air standard assumption, and we use the thermal efficiency equation that we derived just now, you will see that what you get here is slightly higher compared to using variable specific heat, which makes sense, because constant specific heat means that we are assuming the heat doesn't change. The specific heat doesn't change, which it does. So the variable specific heat method will always be more accurate. But of course, because if you use constant specific heat, you will overestimate the thermal efficiency. But you will see that their value actually won't differ too much, which is why both methods are also applicable. So even though I say that this equation you shouldn't use for variable specific heat, you can also sort of use it to cross-check your answer. You won't get the same thing, but at least you can see it should be about the same range. Okay, then after that, MEP, you need to use this work net over V1 minus V2 equation. So we only know the compression ratio. Technically speaking, we don't know the actual volume. So this question actually sub the V2 with V1, then it finds V1 using ideal gas equation again. The R value you can get from the table. Then it obtains the MEP value. If you want to use the ideal gas equation to find V2 also can, but bear in mind that there is a risk where the ideal gas equation, V2, all the properties you find yourself on. So there is a risk that there are some mistakes there. V1 will always be correct because T1 and P1 is given by the question. They are given by the question. So that's why here they just keep everything to V1 and they use the compression ratio. But again, actually same thing lah. You can just use V2 over V1 equals to R, then you can find V2 also. Same thing. Okay, so we are done here. So here, this is where we will stop. Then Thursday we will continue with diesel cycle. Yeah, that one, the name more straightforward, is called diesel cycle. And then I will show you how we can analyze diesel cycle with constant specific heat. So we use one method for each of the cycle, but actually they are applicable for both lah. It's just that I split into two examples to show you faster. Don't need to use both methods than for one cycle itself.